Section 7.2 Equations of states for real gases. For an ideal gas, PV equals nRT. So pressure is simply nRT over V. For van der Waals gas, we know we need to make some corrections. We need to take the attraction into account. The greater the attraction, the lower the pressure. We also need to take the finite size of the atoms or molecules into account. So this V minus MB is the available space in a container, or the void space in a container. So this V is the volume of the container minus MB that give you the available space. So this VDW equation can be used to describe the real gases more accurately than this PV equals nRT. There are some other equations like this RK equation, Redlich-Kwong equation, can be more accurate under some other conditions. So let's look at some real example, like CO2 at 426 Kelvin. This is fairly high temperature. It's roughly 153 degrees Celsius. Now let's look at the experimental data. The black dots are experimental data. And then if you look at the red curve, that's the ideal gas behavior is PV equals nRT, pressure is nRT over volume. So this is actually a reciprocal curve. It's not too bad. But if you use the VDW equation or the Redlich equation, the yellow line and blue line, they fit the experimental data better than the ideal gas law at this 153 degrees Celsius. At 310 K, so this is lower temperature. It's about 37 degrees Celsius, human body temperature. Now let's look at the experimental data, the black dots. If you use PV equals nRT to make prediction of the pressure of the CO2, you will fail. Look at the deviation here. When the molar volume is small, you have a real pressure of roughly 80 bars. But if you use ideal gas law to make prediction, it's roughly 200 bars. Very large error. Okay, again, when the molar volume is really small, you cannot use the ideal gas law because the distance between the gas molecules is too close. There's a huge attraction, there's a huge repulsion. If you use van der Waals equation, the yellow line fits the experimental data better. If you use the Redlich-Kwong equation, well, that's the best. So again, for lower temperature, we have to use a more realistic equation, such as VDW equation or this RK equation to describe a real gas. What if we further lower the temperature? Now let's go extreme case. Let's lower the temperature to negative 30 degrees Celsius. This one is negative 30 degrees Celsius. We start from larger molar volume and we keep compressing the gas. Over here, the pressure goes up. But look, at this point, when the molar volume is about 0.4 something liter per mole, that's very small molar volume, I want to remind you, because at the room temperature, the molar volume is 25 liters per mole. So this is only 0.4. So this CO2 is highly compressed at this low temperature. At this point, the pressure remains constant. How is that possible? Actually, the pressure remains constant only because part of the CO2 gas is compressed into liquid with a very small volume. So when you are trying to decrease the molar volume, you are just converting the gas to liquid. At this point, all CO2 is in the liquid phase. At this temperature, what's the pressure here? Roughly 35. 35 bars, this low temperature, all CO2 becomes liquid. And then if you want to further compress a liquid, okay, you need very high pressure. That's why this pressure shoots up sharply. And then you can also do this experiment at 258 K, 274 K, you can compress the CO2 gas into liquid. What about higher temperature? If the temperature is higher than 304, well, you will not be able to compress the gas into liquid. The temperature is too high. So we call this critical temperature. 304 Kelvin, that's roughly 31 degrees Celsius. This is the critical temperature of CO2. You may wonder, what if I use really high pressure to compress the CO2 gas at a higher temperature? Well, it will become a so-called supercritical fluid. Now let's visualize the compression of CO2. At 258 K, this is lower than the critical temperature, so it's possible to compress CO2 into a liquid phase. First, we have a lot of CO2 gas. We keep compressing. CO2 gas is converted to liquid, more liquid, 100% liquid. At this point, if you want to further compress the liquid, you need a huge pressure. And again, you can do this only if the temperature is lower than the critical temperature. For CO2, it's 31 degrees Celsius. So again, if the temperature is higher than the critical temperature, CO2 cannot be compressed into liquid. So what if you exert huge pressure to this CO2 at a temperature higher than the critical temperature? Well, a supercritical fluid is going to be formed. So if you watch this YouTube video, I can play part of it. You're going to see this is a liquid.
And what is actually
gas.
in here in the picture, there is a liquid sealed into a cell with gas above it. The vapor, like it could be water and steam. It's not water, but it's similar. So if we start heating this.
What did you do just then?
I just flicked this switch and switched on the heater, so the temperature you can see is going up. And as the temperature goes up, this begins to boil. So you can see it begins to boil, and as it boils, material goes from the liquid into the gas. And as it goes into the gas gets denser because it can't escape. It's a sealed cell, but the liquid, because it's being heated, expands. So this becomes less dense, that becomes denser, and eventually they become the same density, and the line in between it completely disappears. So you can see it's almost gone now. And what happens is that you then have a gas which has about half the density of the liquid, and this is a so-called supercritical fluid. And I first saw this demonstrated.
All right, let's get back to the document here. At the critical temperature and critical pressure, delta P over delta Vm, the molar volume, is 0. The slope is 0. All right, so if we go back to the graph, you can see that. Look at this slope. This slope is supposed to be 0. And also, it's less easy to see that the second derivative is also 0. But if we solve these two equations, we will be able to get the critical temperature, the critical molar volume, and critical pressure. All right. So by plugging the parameters A and B, we will be able to get the numbers. For example, for a nitrogen gas, we know A, we know B. We can compute the critical pressure for converting this nitrogen gas into a supercritical fluid. Again, just plug everything in. The result is roughly 34 bars or 33 ATM. So you can look